quite a bit about this on yesterday, and we're gonna just keep talking about it. Mainly learning about how to balance, how to interpret the coefficients and things like that. So the last thing we talked about was this equation right here where we had N2 plus O2 going to N2O5, and we balanced that out. So let's look at some other examples. And in these examples, we're going to apply some other skills too. So we're going to apply, obviously, labeling the reactants and the products. That's important. And the ratio of the first reactant and the second product. So that's going to be this reactant and this product in each example. All right, so let's look at the first example. And it just says balance following chemical equations. All right, so we have KOH, we have phosphoric acid. Let me give you the name because there's another word problem that has phosphoric acid in it. So this is what it looks like. So we've got phosphoric acid, potassium hydroxide, and that's going to give me potassium phosphate. Again, you never get away from naming and nomenclature. It's always going to be a part of the process because that's the language. That's how we speak the language. And this is water. All right. So let's go about balancing this. The best way to do it, again, is to make a list of the atoms. So you got potassium, and sometimes depending on what the what the formula is, I'll keep the polyatomics how they are. But for now, let's not do that. We'll do it in another example because this one is going to get convoluted if we do that. So on the and then we're going to label this. These are my reactants. And on the other side, these are my products. All right. And so we got potassium, oxygen, hydrogen, phosphorus. Those are the atoms that are present in the reactants. And then it's going to be the same atoms in the product as well. Potassium, whatever, oxygen, hydrogen, and phosphorus. So in the reactants, how many potassium atoms do I have?
In the one that you highlighted?
Yeah, on the reactant side, yes.
Looks like one.
Just one, good. And then oxygen, we got 4 here and 1 here. So that's a total of 5. And then hydrogen, we have 3. And then phosphorus, we have, well, actually we have 4 hydrogens. And then phosphorus, we have 1. All right, the hydrogens, you have 3 here and 1 here. All right, and then we look on the other side. We have 3 potassium atoms. We have 5 oxygen atoms, 4 here, 1 here. And then we have 2 hydrogen atoms and 1 phosphorus. All right, so now we need to balance this. So we could start with any of the atoms. If we start with potassium, let's see what happens if we start with potassium. You always want to pick one of the atoms to try to balance first. and then you keep going until everything is balanced. And it's really trial and error. Sometimes what you start out with works, sometimes it doesn't. And sometimes, like we talked about yesterday, you may have to use a fraction or something like that. So let's look at balancing. Let's try to balance potassium. So if we put a 3 here, all right, that's going to make this times 3. So now we'll have 3 potassium atoms. It's going to make the oxygen, it's going to add 3 oxygens, right? So we started out with 5. And now we're going to have, so that's 3, that's 4. Now we'll have 7. Right, so it's not the total plus 3, it's the oxygen and KOH. That is 3 oxygens now plus the other 4 oxygens. So now we'll have 7. So let me fix that up. All right, and then we have for hydrogen, now we have 3 plus 3 instead of 4, right? Because you have 3 here and 3 there. So let's put that in. Now we got 6 hydrogens, and then phosphorus doesn't change. All right. So on the other side, we got 3, 5, 2, and 1. So let's see if we balance the let's balance the hydrogens now, because I think if we do that, then we'll be able to, everything else will line up. So let's do that. So the hydrogens on this side, we have 6 on the reactant side. So let's try and put a 3 here and see what we get. All right, so that's going to be 6 hydrogens there. And then we're going to have 3 oxygens in addition to the 4 that are in PO4. So that's going to be 7. And it looks like we are good. Is that right? So 3, 7, 6, 1. And then over here, 3, 7, 6, and 1. Is that right? Everybody okay with that? So in the balanced equation, it is 3 moles of KOH. The phosphoric acid, the coefficient in front of that is understood to be 1. So that is a 1 there, understood. And then for potassium phosphate, there's a 1 in front of that, that's understood. And then 3 waters. Yes or no? Anybody not seeing that or not following? All right, so let's answer that last question. What's the ratio of the first reactant and the last reactant? So I had that KOH highlighted earlier. Let me highlight it again. So KOH and water, what's the ratio between those two? All right, the way we determine that is to take the coefficients. All right, so the coefficient in front of KOH is 3. The coefficient, it's the Saxton, it's the first reactant, which is KOH on the reactant side, and the second product, which is water on the product side. All right, so it's the coefficient in front of KOH is 3. So it'll be 3 to 3 or 1 to 1, right? That's the ratio of KOH, which is the first reactant, to water, which is the second reactant. Any questions about that?
Why do we need the ratio?
You said why?
Mm-hmm.
That's just a part of the process, because we're also learning that skill of comparing the different substances, like the relative amounts of each substance. So that's just a part of the process, because you're going to need that. If you were converting between moles of water and moles of KOH, you would need that ratio between them. Right? That's the ratios are like conversion factors. So if I gave you 10 moles of water and asked you how many moles of KOH would that be equivalent to based on this reaction, then you would use that ratio to convert one into the other. Right? Remember those coefficients. These are my stoichiometric coefficients. So these tell me the relative amounts of each substance relative to each other. All right, so those are my stoichiometric coefficients. So that's once we get those, then that's how we know the equation is balanced, and that's how we know that what the ratios of each thing is. All right, let's do the next one. It says NH3 plus O2 gas goes to NO plus O2. So the first thing you want to do is take inventory of your atoms. So you have N, A,
Dr. Ross,
go ahead, and O.
sorry to interrupt you. There's Maya's in the waiting room trying to get in.
We don't even have a waiting room for this class.
Well, she just texted me. I'm sorry.
No, we don't have a waiting room. If they just click the link, they should be able to come right in.
Tell her to like redo it, because sometimes you do that to me. Like you be done started the meeting and I've been sitting there for a minute, so then it just won't let me know that you started it, and it'll just have me be like, oh yeah, the host will let me in a second.
Okay, thank you.
So leave and tell her
Yeah.
to restart it.
All right, I appreciate that though. All right, let's do the next question. All right, so we have nitrogen, hydrogen, oxygen. And then we also have on the other side, same thing. The atoms are not going to change, right? Because you don't lose atoms, you don't create atoms, you don't destroy atoms. So still gonna be the same atoms, they're just going to be in different relative amounts. All right, so how many nitrogens do we have on the reactant side? So these are my reactants, and then these are I'm just going to put R and P. I need that room.
You have one nitrogen in your reactants, and then you have your product.
Okay. How many hydrogens?
3 in your and then 2 in
2
your
oxygens.
product. Oh, I was gonna go
I got you.
forward.
I heard what you said. 2 hydrogens over there, and how many oxygens?
1. No, where you see it 2 over here?
There's 2 oxygens, one in NO and one with water.
Oh, got you. I was like, huh? That don't got no subscript. Never mind.
All right. So now let's see if we can balance this out. Let's start with the hydrogens, because there's a common number between them. I think if we can get to 6, then we'll be able to balance that out. So let's put a 2 here, and let's put a 3 here. That'll give us 6 hydrogens on both sides. So let's do that. So this is 3 times 2. It's going to be 6. That's going to change this from 1 to 2. And oxygen hasn't changed. We'll leave that. Okay, so now we'll have here 6. So that's going to be times 3. And then instead of 2 oxygens, now we're going to have 3 plus 1. It's going to give me 4 oxygens. Are we good with that? So 4 oxygens, 6 hydrogens, and then nitrogen hasn't changed, but we got to fix that too. All right, so how do we balance nitrogen? What do we need to do? If we got 2 on the left side, we need to try to get 2 on the right side. Is that right? So what would you do next if we're trying to balance nitrogen now? All right, I'm going to put a 2 here. That's going to make this 2. And then that's also going to add to the oxygen. So instead of 3 plus 1 is going to be like 3 plus 2, because you got this is going to increase that number of oxygens to 2. So the total number of oxygens is now going to be 5. Are we okay with that? So you have 2, 6, and 5, and then 2, 6, and 2. So now we just need to balance oxygen. All right, and in this case, this is a case where you could use a fraction. Right, a lot of times when you have diatomics present, like oxygen gas, chlorine gas, nitrogen gas, it's okay to use a fraction. So what fraction would you put in front of O2 to make that 5? Right, the fraction you would use in this case would be 5/2. Right, and that'll balance this. So if you do this, the 2's are going to cancel. You're going to get 5. So now you can see that you have 2 nitrogens on both sides. You got 6 hydrogens on both sides, and then 5 oxygens on both sides. Sometimes when you have, again, we have those diatomics, you have to use a fraction to balance them out. All right. Questions about that one? All right. Let's go to the next one. We have aluminum plus oxygen gas giving us aluminum oxide, right? And for this one, let's go ahead and, so we got 2 aluminums. One aluminum, 2 oxygens. And over here, we got 2 aluminums and 3 oxygens. What number could we kind of have in common with both sides that we could get to? What do you think? Because again, balancing is like it's kind of like an art. Sometimes your strategy is straightforward, other times it's not so straightforward. But the goal is always the same, to get the same number of atoms on both sides of the equation. What could I do? What number could I use to balance both sides out? All right, let's think about this. What if I put a 2 here? What would that give me?
It'll give you 4 aluminums and 6 oxygens.
Good. So that'd be times 2. Hold up. This is times 2 for 4, and this is times 2 for 6. Good. Now, how do I, on the other side, this is cake now, right? Because aluminum is by itself. So I can just put a 4 here and it doesn't change anything else except for aluminum. What do I need to do to oxygen to make it 6?
Put a 3.
Put a 3 in front of it. So now everything is balanced. This is times 4. This is times 3. And now everything is good. So sometimes when you approach these problems, especially a problem like this one, where you have the aluminum and the oxygen separate and there are no other atoms, like it's not a compound, it's just the element itself, then that makes it a little bit simpler to balance these equations. Other times you may have to use a fraction when you have those diatomics. In this case, you didn't. All right, let's go to the next one. Gold sulfide and hydrogen gas gives us gold and then hydrogen sulfide or dihydrogen sulfide. All right, so let's do our inventory. We got, let me change colors. We got gold, 2 gold atoms, sulfur, 3, hydrogen, 2. And then over here, we got gold, 1, hydrogen, let me keep them in order. Sulfur, 2, and hydrogen, 2. Sulfur is 1, sorry. Mine is somewhere else. All right, what can we do? How can we fix this? We could start out by balancing let's start out balancing the sulfur. Let's balance the sulfur. Let's balance the sulfur. If we put so we're going to start out trying to balance sulfur by putting a 3 here. Right? So that's going to give me 6 hydrogens and 3 sulfurs. Is that right? And then now let's balance hydrogen, because now I think we're in a good spot. We got 3 here, 3 here, and then we have 6 here, and we got 2 here, but we can fix that because again, this is by itself. It doesn't change anything else. So what would I put here to get that to 6?
A 3.
Put a 3. And then this will be times 3 No, so that's 6 hydrogens. And now we just need to balance the gold, and that's easy because this is also by itself. So we'll put a 2 here. This is times 2. So now it's all balanced. And again, the purpose of balancing, again, is you could have started with gold, Saxton. You still would have ended up working your way down through the rest of them. But I think, again, it's a strategy. So sometimes if you start with the right atom, then it makes less work for the rest of the problem. But if you start at gold, then you have to work your way through to the other. You're still gonna have to work your way through the other atoms, because once you balance that gold, that would be it. So we started with sulfur. That's why I started with sulfur, so we can touch 2 of the atoms at the same time to see if we could see how that would affect the reactant side. Right, so it's all strategy and it's trial and error. So, and it takes a lot of practice. But not necessarily start with the hardest one first, but it just, again, it's like it's trial and error. I started with sulfur because it was an odd number, because it had a 3 there. And I saw that if I put a 3 in front of sulfur, it would give me 6 hydrogens, and then I could easily balance the H2, because all I had to do is put a 3 in front of that, and that'll give me 6 hydrogens on that side too. So I end up balancing 2 atoms at the same time. All right, let's do another one. Let's do one. Let's actually, we're going to come back to some of these. I want to work through a couple of these word problems, because this is really, really important to be able to go from the words to the actual chemical formulas. All right, so we have aluminum bromide and chlorine gas, and they react to form aluminum chloride and bromine gas. This is a good one. What is the formula for aluminum bromide? What do you need to know in order to write that formula? Right? If you think about it, this from a periodic table perspective, right? Aluminum is in group 3. So this is going to be Al3 plus. Bromine is in group 7, so that's Br minus. And then chlorine is a diatomic, so it's always going to be written as Cl2. Chlorine gas is going to be written as Cl2, because there are 7 diatomics. It's hydrogen, nitrogen, oxygen, and then chlorine, fluorine, bromine, iodine. So that's that. And then over here, same thing. This is group 3, group 7, and then this is, sorry, not squared. All right. So now, what do? How do we put these together? Aluminum and bromine, or bromide. How do we put those together? What's the method to write out the formula? Then we do this, crisscross the charges, so we'll know what the subscripts are.
Yes. Wouldn't it be AlBr3?
Yes. Plus Cl2. So that's these are my reactants. I'll have an arrow showing that a reaction is taking place, and you're gonna do the same thing here, right? So it's gonna be AlCl3 plus Br2. All right, so when I look at this, I kind of sense that we could deal with the number 6 and balance it. So let's see what we can do. So we got aluminum, bromine, and chlorine. You got 2 chlorines, 3 bromines, 1 aluminum. On this side, aluminum, bromine, chlorine, 1 aluminum, 2 bromines, and what the heck is that? 3 chlorine. All right. And the question is now, how do we balance this? Why did I put bromine in there? All right. How do we balance this out? So what can we do to which atom do you want to start with? Let's do that. I'm thinking we can start with chlorine on the right side. Let's do that. So let's see what happens if we put a 2 here. Right, that's going to make aluminum times 2. So that's going to be 2 aluminums. Chlorine is going to be 3 times 2, which is going to be 6 chlorines. And then bromine is still 2. All right. So now let's balance the chlorine on the other side, which since it's by itself, that makes it much easier because all I need to do is to get that up to 6 is to do what? I'm going to put a 3 here. So that's going to be that times 3 is 6. All right. Now I need to balance the bromines. Let's do that. Or actually, let's just balance the aluminums. And then that way we'll touch bromine as well. And we can figure out what to do with that Br2. So we got 2 aluminums on the other side. So we're going to put a 2 here. All right, so that's going to be that times 2. And that's also going to increase the number of bromines to 6. All right, so what do we need to do on the other side to the Br2?
Put a 3 in front of it.
Put a 3 in front of it. And that'll take that up to 6. All right. Let's do that second one and then we'll stop. We got to stop. So calcium hydroxide. Calcium is in group 2. Hydroxide looks like this. Well, right, and that's a -1. It's a polyatomic and it has -1 charge. And then for and it's reacting with phosphoric acid, which we saw up front. But let me show you how to put that together. So this is H plus, and then the phosphate anion is PO4 and it's -3. So that's how we end up top. We had H3PO4. That's where it comes from. And then over here, we're going to have calcium phosphate, which is Ca2 plus, and then PO4 -3, and then water, which is H2O. All right. So now let's write this out. So it'll be CaOH, and there's going to be a 2 down here. I'll put it in parentheses, CaOH2, and then plus H3PO4. And that's going to give me Ca2 PO4 3 plus H2O. All right, so in this case, this is a really good place to introduce a kind of a slightly different strategy. Because if you look at the PO4, the phosphate anion is kind of the same on both sides. And we could try keeping that intact, like keep the polyatomic intact. And by the same token, we can do that with the OH as well. So we can say water is H, OH, like that. All right. And so let's try that strategy to see if that makes balancing this easier. Because sometimes we pull those polyatomics apart that have a lot of atoms in them like that, it makes balancing a little bit more difficult.
Dr. Russell,
Go ahead.
for calcium phosphate, why wouldn't it be Ca3PO42?
It is.
Like with the
It is. It is.
Oh.
It is. My bad. All right. Good. Thank you. All right. So let's see what we can do here. Let's see if we can balance this by we're going to keep the PO4s together. So we got calcium and then OH. We're going to keep that together. We're going to keep the PO4 together and then H. And over here, we're going to have the same thing, calcium, OH, PO4, and H. So over here, we have one calcium, we got two OHs, we got one PO4, and then we have three H's. And over here, we have, keep in mind, I'm not counting the OH proton or the hydrogen with the H. So we got one H here. We have one OH. We have three calciums. And we have two PO4s. Are y'all following that? Any questions about that?
no.
All right. So now let's see what we want to balance first. We could start with, let's start with the calcium. Let's start with the calcium. Let's start with the calcium. So if we do let's do a 3 here. That's going to be this times 3. And that's also going to be this times 3. So that's going to give us 6 of those and 3 of those. Keep in mind, we're keeping the polyatomics together on purpose. It's rather than breaking them apart and doing atom for atom. And it's, again, it's a nuance to the original strategy. All right. And then we still have one PO4 and then 3 H's, like single hydrogens. All right. So then if we do that, let's go over here and try to balance the OHs, because we just balanced the calciums. Now let's balance the OHs. So let's take this and put a 2 in front of it. We need a 2 or 6. We need a 6. We need a 6 in front of it. So that's going to be this OH times 6. And then this H is also going to be times 6. Right, so now we got 6 hydrogens, 6 OH groups, and we got 2 PO4s and 3 calciums. All right, now, do you see it? You see the light at the end of the tunnel? What do we need to do to finish this off? Sorry about that. I don't know why I'm getting the facts. What do we need to do to finish it off? We want to if we balance the hydrogens, we're going to at the same time balance the PO4s too. So let's balance the hydrogen since we got 6 over here and we want 6 over here.
You'll put a 2 in front of it.
2 in front of it, and we home free. So this is going to be this times 2, which is 6. And then the PO4 is going to be the whole thing times 2, which is going to be 2. So now if you look at the total for each side, right, you got 3, 6, 2, and 6. And over here, same thing, 3 calcium, 6 hydroxyls, 2 PO4s, and 6 hydrogens. So sometimes when you have polyatomics like phosphate or nitrate or polyatomics like that, it's easier sometimes to keep those together than to break them apart into their atoms. If we had broken this apart into all the atoms that are present, we'll still be balancing, right? But the fact that we kept the polyatomics together when we were balancing made this an easier problem to complete. So it's a nuance, and you have to know when to do it and when not to do it. But this was a case, and that's why I did this example. This was a case to do it because that phosphate is rarely going to break up into its components. It's always going to stay PO4, right? Nitrate, if you're using NO3 or NO2, sometimes that can, on the other side of the arrow, it may be different, but some of those polyatomics, they rarely break up. So you can keep them together and just count them as a unit instead of trying to break it into 1 phosphorus and 4 oxygens, right? So in this case, I'm gonna write this here. Right, we kept the polyatomics together and we just balanced it that way. All right, we got to stop. We are 6 minutes over time. I apologize for the delay earlier, but yeah. Go ahead, Saxton.
I was gonna say, before you let us go or let me go, can I get like, I don't know, topics on chapter 3? Because I didn't even think about it as chapters for real. I was just thinking of like recitations for real. So
That's not funny. Chapter 3 was, let me see.
Okay, we have, moles, molar mass, we
Yep.
have percentage,
Empirical formulas and molecular formulas and molarity.
empirical and molecular. Hold on.
Yep, formulas, which dealt with percent composition.
Yeah.
And molarity. And really that was it. I mean, it doesn't sound like a lot, but we did a lot because we did a lot of percent composition problems, and we also did a lot of molarity problems too.
What about percent abundances?
That was in the first chapter.
Okay.
Yeah.
See, there's literally like my notes have no kind of organization.
We got to get some organization in there, Mike, so you can.
It's like recitation week 5, and then there's test 2, and then there's questions, examples. It's weird.
We got to get some organization. Go back and look at the notes. I post the notes from every class on Blackboard.
Yeah. And organize and go through.
Got it. Go and get the notes. It's in the course notes content area on Blackboard. I post the notes after every class. So go and look at those notes and see how they're organized, and then you'll know how to organize your notes.
And study. Thank you.
All right. Have a good day. Y'all take care. See you on Monday, God willing.
All righty.
All right.
Thank you. Have a nice one.
You have a good one.
All right. Zion, don't forget Monday. We need a serenade.
Thanks for reminding me. I got you.
All right.